Okay, so recall that your inner ear, right, consists of the medial aspect of the oval window, right, which is what the stapes is poking into on its lateral aspect in the middle ear, and the cochlea, which is that coiled structure. And it's really quite interesting. This structure, is encased in bone, except for the oval window, which is flexible, right? And we're going to see there's another window, another flexible membrane that allows for the energy, after transiting through the cochlea to kind of escape back into the middle ear. It's called the round window. So there's only a couple of little flexible kind of membranes that provide any kind of access or egress of energy, from this kind of bone encased structure. Actually, it's really interesting in a skull, and I'll show us in our scheduled classes. We actually have these kind of bubbles of bone. They're called bulla, auditory bulla, in which the cochlea kind of sits on the base of the skull. So it turns out that, remember, you've got something vibrating out here, right? Pattern of compression and rarefaction of the air is working its way towards your ear, gets captured by the pinna, all those whorls and channels, gets funneled down the auditory canal, hits the lateral aspect of the tympanic membrane and causes it to move. So now we're, through our outer ear component. Now we're on the medial aspect of the, eardrum, which is attached to the malleus, the incus, and the stapes, those, collectively known as ossicles, the three little bones, including the smallest bone called the stapes, which is going to be pushing in at the oval window, the lateral aspect of the oval window, the entrance, to the cochlea. And that middle ear, that serves to amplify, to concentrate, to, really enhance, the poking, basically into the cochlea. And then movement of that oval window is going to create waves inside the cochlea, which is filled with fluid, something called an endolymph, which will cause a membrane that runs down the middle of the cochlea, all the way from the base end, or the basal end, all the way out to the apex, or the apical end at the tip. And this basilar membrane is going to move in response to sounds of different frequency and amplitude. So there is a tuning of that basilar membrane. So its actual physical structural components vary from the base end to the apical end. It's kind of narrow and stiff at the base end, at the entrance of the sound wave information, right, at where the stapes is poking, at that oval window. The basilar membrane at that basal end or base end, right at the start, is narrow and stiff and tends to move and vibrate in response to higher frequency sounds. And as you move down along that basilar membrane, its actual physical characteristics change. It becomes wider and floppier and more responsive to sounds of lower frequencies. So high frequency, sound detection occurs at the base end, the narrow, stiff base end of the basilar membrane within the cochlea. And then as you go out further, towards the tip, you're going to get to wider and floppier, basilar membrane, and it's going to be more responsive and move in response to, lower frequency sounds. And sitting on that basilar membrane are what we call hair cells. There is one row of, what are called the inner hair cells. They're working their way down that basilar membrane. And then there are three rows, that are, adjacent here, going all the way down from the base end all the way, going around and around to the apical end, of what we call outer hair cells. And overlying the basilar membrane, the base membrane, the basilar membrane upon which these hair cells all sit, is this kind of gooey membrane. It's actually mucousy and gooey. There's a lot of goo and kind of mucus in our auditory system, surprising amounts in auditory and vestibular systems, actually. And it's called the tectorial membrane. And the outer hair cells, the three rows of outer hair cells, and there are about 15,000 outer hair cells per ear that sit along the basilar membrane in these three rows. Their hairs, these are called stereocilia that stick up here, are actually stuck, into the overlying gooiness of the tectorial membrane. So the outer hair cells are sitting in the basal membrane in 3 distinct rows, and their stereocilia, these hairs, these kind of membrane-bound components here, are stuck at the top into this overlying gooey tectorial membrane. It's about 15,000 per ear. And there are only about 3,500, in the typical adult left, after we've knocked a few of these off by loud sounds, of what we call the inner hair cells. And these have, stereocilia tips here that are actually free, that are in this fluid called the endolymph. And they can move back and forth with the movement of the basilar membrane. These are called inner hair cells. We're going to see that they're heavily innervated by the vestibulo-cochlear nerve, the vestibular division of the 8th cranial nerve. So this weird little hair cell, basically we're going to see the inner hair cell can move in response to the movement of the basilar membrane, which, remember, is going to be dependent upon the frequency of the sound, where along that basilar membrane you get movement, right? And we're going to see it's going to respond to that movement by the release of neurotransmitter here onto, what's effectively a dendrite, of, cells that are going to form the vestibular, component, vestibular division of the 8th cranial nerve and carry that information back. About 95% of the, vestibular division of, cranial nerve 8, which is the vestibulo-cochlear nerve, is going to carry information back into the central nervous system from these inner hair cells. So we say that these inner hair cells appear to be the primary sensory neurons for audition. But very interestingly, about 5% of that nerve, of that particular division of the 8th cranial nerve, is actually going the other direction. It's coming from the central nervous system. It's an efferent output, and it's going to synapse and release neurotransmitter onto the outer hair cells, those 3 rows of far more numerous, outer hair cells. And we'll talk more about the role of those outer hair cells. They appear to dampen and amplify sounds by actually physically expanding and shrinking, pulling the gooey tectorial membrane down, allowing it to move more. They actually are allowing, some kind of a tuning, of the cochlea, in different auditory environments. So there's an efferent component, that influences the physical characteristics of the outer hair cells. The inner hair cells, however, again, are the primary sensory neurons, for